Hello, ladies and gentlemen. A very good morning to you. As you can tell by my window, it is very much the morning. I've been working on this since 4:30 in the morning, just for you. Um, Hope you guys are self-quarantining well and staying safe, and being smart. So, what are we talking about today? So, today is incredibly important. This is the stuff that you're going to see in college chemistry as well. Um, This is the stuff that in my chemistry 1 and 2 college labs we used almost exclusively. Um, so I'm also going to try a slightly different format of notes where instead of taking up so much time writing it, I've already written it, and then I'm just going to show you the notes as we get to them. So if at any point I'm moving too fast for you to copy, please pause the video. So first thing we're talking about, and also, we're not covering as much ground today. This is important enough of a topic where I think we should slow down a little bit. We're only covering between pages 321 and 323 today. So just three different pages. So what we're talking about today is something called colligative properties. Okay? And this is a property that changes when a solute enters the solvent. Okay? Colligative properties are a property that changes when the solute enters the solvent. And to explain this and to put it in the real world, so think about the ocean. Okay, we're at Myrtle Beach, sort of, if unless you're in Conway, but we're basically in Myrtle Beach, right? Why doesn't the ocean evaporate in the sun? You have a puddle on the ground, maybe you spill your Dr. Pepper in the parking lot, and within a couple of minutes when the sun's out, it's gone. Why doesn't the ocean do the same thing? Why don't we wake up, go to the beach, oh shoot, the water's gone. It evaporated in the sun. Why doesn't that happen? What's the difference between a puddle and the ocean? Well, an interesting experiment that we could do. Hmm, we might have an experiment to do on Wednesday. But if you took a glass of salt water and a glass of normal water and put them both in the sun, the fresh water would evaporate way faster. Why? Because when you put a solute in your solvent, it completely changes the properties of it. So the salt is almost acting like a barrier for the water to get out. The water wants to get out with the sun. Stuff in the water is going to bring it down. Um, so that explains the vapor pressure. It'll change the boiling point and the freezing point. Why doesn't the ocean freeze when it's cold enough to snow? Because the salt changes the freezing point. It isn't until you get way north or way south that you end up with parts of the ocean freezing. But even then, it's not all of it. So, colligative property is a property that changes when a solute enters the solvent. Case in point, the ocean. Vapor pressure. Vapor pressure, basically, this isn't a great definition of it. This is more an explanation of it. I just kind of explained vapor pressure. Um, when you think about the salt water, the, when the water heats up, all the water molecules want to do the H2Os. They want to go up, right? They want to go up into the air and fly away, and be free. Um, but that salt present is sort of acting like a barrier or a shield to where the water can't quite break up through it. The salt is almost weighing it down, holding it down. Um, so the vapor pressure is how much it takes for that water to be able to come up. In other words, the higher the concentration of salt, the more salty the water, um, the more it's going to take for that solvent to actually get out. Boiling point elevation. So this is the one that you're going to see a lot in chemistry moving forward. It's our new best friend. So boiling point elevation is the effect, whether going up or going down, that solutes have on the boiling point of substances. The effect up or down solutes have on the boiling point of substances. And a rule you can follow, and as you can see, it's a tricky rule. Uh, Trips up the best of us. Is that the lower your vapor pressure, the higher your boiling point. Lower your vapor pressure, the higher your boiling point. Um, so some substances will boil at 100 degrees. Some substances will need to boil at 200 degrees. Um, some substances we can't even make boil because the boiling points are so high we can't get to them. Some boil at normal temperatures. It depends on what's inside of it. So now we introduce the math, and it's the reason I'm slowing down today a little bit because it's kind of weird. You have a lot of new variables that you've never seen before. So how do I manage this? The first variable we're going to talk about is delta TB. What do you think that is? B is for boiling point, T is temperature of boiling point, and the triangle means change. So this is the change in boiling point. Okay, this is piece number one. The change in boiling point you would find by subtracting the original boiling point from a new boiling point. So if I told you that um, the boiling point of water used to be 500 degrees, um, I don't know, the boiling point of chemical X used to be 500 degrees, um, but then we added a bunch of salt and now it's 600 degrees. How much did it change by? You'd say, oh, 600 degrees minus 500 degrees. It changed by 100 degrees, so that would be your change in boiling point. Not super complicated, but yes, very important. So the second thing we're going to introduce is KB. Now, KB is, do you remember in the gas laws section? We had temperature, which changes all the time, pressure changes all the time, volume changes all the time, and I said we need a constant to keep it consistent. Well, it's the same thing here. Um, there is a boiling point constant, more specifically, a molal boiling point constant for every single element and for every single compound. Um, and the standard one for water is 0.512 degrees Celsius. Um, you'll see why this is important later, but it keeps the equation grounded in reality. Um, these will either be given to you in a table, in a problem, or you'll be solving for it. But I wouldn't worry about it too much. All you need to know is what it is. That delta TB is the change in boiling point. KB is the molal boiling point constant. Um, and um, we had R in the gas laws, and we sort of said it was at STP, right? I said it was the STP machine, I think I said. Um, KB is similar. This is where the molal comes in. If you had 1 kilogram of water with 1 mole of solute, kilograms and moles, right? That's molality. 1 kilogram of water with 1 mole of solute, that would raise the boiling point by 0.512 degrees Celsius. Um, if you had a kilogram of water and you put in 1 mole of sugar, then that would raise your boiling point by half a degree Celsius roughly. Um, that's how that works. So, a general rule we can follow is that the higher your concentration, the higher your boiling point, um, which is similar because the higher the concentration lowers the vapor pressure, but it raises the boiling point. The lower the vapor pressure, the higher the boiling point, the higher the concentration, the higher the boiling point. The more crap you put in your water, the harder it's going to be to boil that water. Okay? So here's how we're going to put all these pieces together in one masterful equation. Hallelujah. So, as I flip my page and get ready to show you an example, let's explain this. So this is said, the change in boiling point equals the molar boiling point constant times the molality. Okay? These are the three pieces we're going to be working with today. So I would write this down, this little bottom section, please, and highlight it. There's a reason I'm using different colors because I think it's important, very important. This is what we're going to be working with largely. So if you need to pause the video and go look over your molality notes, that might be a good idea, because with a couple problems, we're going to be needing to solve for the molality and then plug it into this equation. So that's going to be relevant. But if you're ready, I'm ready. Um, let's look at example problem 12-8. And let me get a fresh piece of paper. Oh, if I can find one. There it is. So looking at 12-8, it says, what is the boiling point of acetone when 0.500 moles of naphthalene, there it is, naphthalene, and I'm just going to write the chemical because it's naphthalene is too long of a word, is added to 1 kilogram of acetone. And it tells me that the molar boiling point constant, which we said was Kb, so Kb of acetone is 1.71 degrees Celsius per mole, or per molal. There we go. So this is my first This is my first problem. What's the boiling point of acetone when half a mole of that naphthalamine is added to a kilogram of acetone? And then it gives me the Kb. So what's my equation? If you want to pause this and try to work through it yourself, that might be conducive to your success, but to each their own. Here's your equation. What am I given? Well, it gives me Kb, right? I have Kb. Does it give me a change in temperature? I don't see one. Does it give me molal? Well, what is molal? Molality is moles per kilogram. Do I have that? Ooh, 1 kilogram, 0.500 moles. I do have that. What's 0.500 over 1? That's just 0.500. So I do have M. M is 0.500. Great. Well, then let's plug in my numbers. So, change in boiling point equals 1.71 degrees Celsius times 0.500. Great. Does anything cancel out here? Units-wise? I see an M in the denominator and an M in the numerator. Those two things are going to cancel out, leaving with temperature. So what is this going to equal? 1.71 times 0.500. I already solved this, so I got 0.855 degrees Celsius. So what does this mean? This was the change in boiling point, right? So if this was the change in boiling point, and this is a positive number, right? That means it went up. So if this is a positive number, if this changed the boiling point, this is the change, this isn't the boiling point. This is just how much it changed. So what's the original boiling point? Well, the original boiling point, if I look on page 322 where I'm getting this problem, it's got a table right there. And I'm looking for, I literally already forgot what we're working with, acetone. So if we're looking at acetone, there's the normal boiling point, A, and it looks like that is going to be 56.2. So if the original boiling point was 56.2 degrees Celsius, and I changed it by going up this much, then what's my new boiling point? Well, I would just add those. And that is going to be your answer. Which I'm not going to write, but you should. And I'll be checking for that in your notes, so make sure you finish that problem on your own. So, by and large, what did we get done? It asked for the boiling point. So we used the change in boiling point equation. We plugged in our numbers, right? We plugged in the constant and we plugged in the molality. That gave us the change in boiling point. Once we found the change, we combined the change in boiling point with the original boiling point, and that gave us the new boiling point. Hopefully that makes sense. If it doesn't, you know where to find me. Um, Next page and last page. Example 12-9. So 12-9 says, if 425 grams of magnesium chloride are added to 675 grams of hot high quality H2O. What's the boiling point? Or what's the new boiling point? If you haven't noticed, when I read word problems, I put them into my own words. I'd recommend you do that too. It very much helps when you're actually trying to solve it. So, what's our equation? Our equation is change in boiling point equals the constant times molality. What do they give me? Well, I have grams of this, and I have grams of that. So how do I do this exactly? So the first step, if we look at units, right? Where's my notes? If we look at units, where do we see grams coming in? Does grams have to do with boiling point change? No. Does grams have to do with the constant? No. The only thing we see grams in is in the molality. So it looks like for this question, we're going to have to actually solve for the molality first. So now would be the good time, like I said earlier, to check in your molality notes as to how exactly to solve for molality. But unfortunately for you guys who hate stoichiometry, that's how you do it. So let's set up a little stoich table. Which one's going to be the solute and which one's going to be the solvent? See if you can guess which one is in your head. I told you that generally, the bigger one is the solvent. So that one's going in the bottom. So I have 675 grams of high quality H2O in the bottom, and I have 425 grams of magnesium chloride in the top. Stoichiometry. So what am I doing first? Well, you can do this in a couple different orders, but for molality, it's moles over kilograms. And the first thing I'm noticing is that this is not in kilograms. So I want the denominator in kilograms, because that's the first thing I want to do. If you want to do this in a slightly different order, that works. So if I want to go from grams to kilograms, I'm going to put 1 kilogram here. How many grams are in a kilogram? 1,000. Cool. So that should get rid of my gram unit. Cool. So my denominator's in kilograms. Cool. I'm good to move on from there. So now I want to change my numerator. My numerator's in grams. I don't want it in grams. I want it in moles. How can I go from grams to moles? If I want to go from grams to moles, I have to put the moles over grams, and I use the molar mass. So what's the molar mass of magnesium chloride? I saved you some time and I already found it. It's 95.21 grams. And now I can cancel out grams of magnesium chloride, and I'm left with moles in the top, and I'm left with kilograms in the bottom. That's exactly how I want it. So I am done here. So what do I get? If I multiply 1,000 times 425 grams, oh, I'm sorry, no. Obviously, we got rid of grams. If I multiply my 425 times 1,000, I end up with my brain is short-circuiting, I'm sorry. I end up with 425,000 over 675 times 95.21. I need to get a calculator because I actually didn't write this out for some reason. Let's do it together. 675 times 95.21. Whoa. That's going to leave me with 64,266.75. Then if we divide those together, 425,000 divided by 64,266.75, we get 6.61 moles over 1 kilogram. So we found our molality. Yay! So now we have this piece of the equation. Hooray! So, now what? Do we have either of these pieces? Well, change in temperature, I have no idea. That's what we're looking for, the change in boiling point. Kb, the constant. What is this right here? What's our solvent? Do we maybe have the constant for that solvent? Yes, we do. I gave it to you on the last page. So now that we have our pieces, let's plug it into the equation. My change in boiling point equals, what did I get for Kb? Kb, I got 0.512 degrees Celsius over molality times, now this is where it's going to get annoying, okay? And I already know this is going to instantly fry some of you guys' brains. Please turn off your smoke alarms before listening to this. So 6.61 was the molality, right? For these problems, there's a really weird step we're going to have to make. So for MgCl2, when this boils, this stuff's going to break apart into an Mg, a Cl, and a Cl. If that's true, how many moles do we have altogether here? A mole of Mg, a mole of Cl, and a mole of Cl. That's 3. Which means that for this number, I'm going to have to multiply this times 3. I know it's gross, but it is what we have to do. I'm going to factor it into my equation over here. No, I'm not. So 6.61 molal times 3 gives us, I believe, 19 point something. Yeah. This is going to give us 19.8 molal. So I know this is going to fry your brain, but Just remember this is one of the steps. When you write your molality, you're going to have to take into account how many moles you're going to have when this breaks apart. If you have 3, you multiply by 3. If you have 2, you multiply by 2. If you have 5 different elements together, you're going to multiply by 5. So you have 19.8 molal. Your molality cancels, and your answer is going to end up being 10.1 degrees Celsius. Okay? Last example, and then we should be good for today, and I'm going to give you guys some similar problems so you can practice this. 12-10. It asks, what's the molality of NaCl in water if your change in boiling point is 0.400 degrees Celsius? What's the molality if your change in boiling point is 0.400 Celsius? Okay, so what's our equation? Change in temperature equals Kb times m. Pause the video and try to do this yourself, because I don't think this one's very hard. I hope you do. That would really help you. What's the molality? If we're looking for molality, I need to rearrange this equation. If I want molality by itself, I'm going to divide both sides by Kb. So my new equation would be m equals change in boiling point over Kb. That's my new equation. Now what do I have? Well, I see water, which means that my boiling point, or I'm sorry, my molal boiling point constant is going to be 0.512 again. I have my change in boiling point. That works. Um, so remember how last time when we had 3 different pieces, we multiplied it by 3 to get it, to get the molality? Well, weirdly enough, it's going to be the opposite here. When we're working backwards to get to molality, we're going to end up dividing by that number. How many pieces do I have here? I have 2. So instead of multiplying by 3 to get instead of multiplying by 3 to get the molality, here we're going to be dividing by 3 to get the molality because we're solving for it. So, right, come on brain, get together. So, my M equals my change in temperature, change in boiling point, which they told me was 0.400 degrees Celsius, divided by Kb, which is 0.512 degrees Celsius over molal. So once I solve this, I get 0.781, and then because there are 2 pieces here, NaCl, I'm going to end up dividing this by 2. And when I divide this by 2, I end up with 0.391, and that's my answer. So the multiplying by 3, dividing by 2 piece, I think ooh, I almost pulled my headphones off. I think that's the part that's going to give you trouble if anything does, which is why for homework, instead of having you do the section review problems, I wrote some of my own that I think will help you a lot more. So I have come up with 3 questions that are similar to the 3 I just did for you. And I'd recommend, instead of just rewriting these, just when you're doing your homework, pause the video on the problems and then solve them from the computer as if you were solving it from the book. Um, so for the first one, you're looking for the boiling point. For the second one, you are looking for the boiling point. And for the third one, um, you were looking for the molality. Okay? I guess the way to remember the multiplying and dividing numbers are you could have really factored this 3 into the problem. So when you're solving for boiling point, you could think that you multiply, and then when you're solving for molality, um, you could have written it here as well. You divide it. That's a way to remember that. But this will give you some practice. And then there are 3 short questions in 12C review that I'd like for you to do as well. So just 6 problems. Um, if you need help, I'll be available over GroupMe today. For most of today, I should be reachable. Um, other than that, I'm thinking we're going to have a online quiz Wednesday during our normal class time hours. So make sure to let me know if that is for some reason not going to work for you, and we can work around it. But the idea is I would have 2 questions. I'd have maybe a question on molality, a question on molarity, and then a question on change in boiling point. Maybe 2 questions on boiling point. So 4-question quiz. Molality, molarity, boiling point, boiling point. Um, so that's probably going to be Wednesday. So I'd encourage you guys to work out any kinks you have on this, ask any questions you need to ask on this, and get these homework problems done. Um, and I'll have a video explaining them up tomorrow, um, along with the video tomorrow morning. But other than that, um, good luck, you guys. I hope you have a wonderful day, and stay safe. Bye.